All right, my friends, let's get this party started. Okay, so let's in terms of like what's happening, not much in terms of announcements or anything right now. Just kind of the same old. Um, yeah. So, well, let's ask some questions. So I know that there was some chatter going on around about some of the homework stuff. But is there any questions that anybody has any right now that we can like address or anything? There's probably there's a little bit of a bleed, and so some of the stuff we'll hammer all that. Anything else that will get hammered out today that we didn't cover that's still there yet. So yeah, we'll definitely address that. But we can also do this like so. I'll try and do this at the beginning of every single class. It's like we'll stop and we'll spend a little bit of time answering those questions. So let's like for those things that you feel like that we haven't covered yet. Let's go through and cover those today. And if it's still fuzzy, and then you take a look at the homework and take a whack at it. And if it's still fuzzy, then we can work on it on Thursday. We can address any of those kind of questions. But if there's something that's like we need to go over, I'm happy to talk about it right now as well. Okay. Cool. Well, let's move on for right now. But like I said, like what I'll try to do is at the beginning of classes, like we'll have that time to answer questions like about anything that's like not clicking or we can take the time to address that. So yeah, no real announcements for today. But what we're gonna be working on today is so we're gonna wrap up decibels, which is gonna be the chapter 2 stuff on levels. And then we're gonna talk a little bit about weighting and then measuring sound level and just talking about just sound levels in general. So this one is like, and I am well aware. Okay, wait, actually step back. So that's going to be chapter 2 stuff, and then we're going to be doing chapter 3 next class. So chapter 3 is a really short one. So we're just spending one day on it. We're going to hit the highlights on that one. This one, I get it. Like on chapter 2, the decibels and levels, this stuff is confusing, and I know it is. I can feel it. It was confusing me for a really long time too. So I know I'm sympathetic to that, and so I get it. And I know it maybe seem like I'm spending a lot of time on the math here, but it's one of those things that like if you start to dig into it and you start to kind of get used to it, it does help. But that said, beyond this course, like you may be like, well, or I guess beyond these lectures, you may not remember how to do all the math all the way through for the rest of your life, and that's okay. There's a few things that I just really want you to remember. Well, namely that decibels are comparison, and I want you just to stop when you see a decibel. What I want you to do is I want you to stop and go, what is it comparing? What are the two things we compare here? And when you start to think about it more, kind of in those terms, it becomes a lot easier to understand how decibels work. The math is useful and it's incredibly important. I use the math all the time in my work, doing things like gear and attaching gear and making sure that all the levels between each piece of gear is behaving the way it's supposed to. Or when you're troubleshooting something like a live sound rig out in the field and you just hook up a multimeter on, you go like, something's not right here. And things like it can really lend itself to explaining why. Like if you have a XLR cable, for instance, and you have one of the pins broken inside of the XLR cable, like a cable came off, you're going to get a 6 dB drop. And you can tell, like you can measure that with a multimeter. You're like, oh, I've half the voltage. That means I have a 6 dB drop. And you can use it for a lot of troubleshooting reasons. So there's a lot of reasons to understand the math behind this and the actual voltage. But really, I mean, the things what we want to talk about, like the reason I want you to remember, the things I want you to remember are that decibels are a comparison, and also to consider what are those comparisons. Like when I'm comparing two things, what is it? So when I say this is 45 dB SPL, what does that actually mean? Remember, every time we see dB or decibels, it's always a comparison. So what is it comparing? And that's the thing to think about. And then also to think about the understanding that it's on a logarithmic scale because we hear and perceive, our perception works on a logarithmic system. So those are the kind of things that I want you to remember, like the true takeaways from this class. The getting down and dirty with the math is like, I know, a little bit kind of a grind, but like it's worth it. I think it's pretty neat stuff. So in the book, I'm spending a lot more time on just the mechanics of the decibels and not so much on like actually doing these decibel problems. There's a few decibel problems that we're working on, but like if you look in the back of the chapter of that book, or I guess the last part of the chapter of that book, it goes through and it does a bunch of different example calculations, and those are really cool because they show you the practicality of using decibels in your like daily life as an audio engineer, and the range in which those questions can be used. So, but we're not going to go through all this because those are like, I won't say there's edge cases. Those are just like, if we were digging in and really drilling down, we'd spend more time on it. I used to teach a class called maintenance and calibration, and we spent like half a semester on decibels. Everyone was like dying, but at the end of it, everyone's like, dude, that is so cool. I totally get this stuff now. So, but we'll talk. So we're gonna crank through some decibel stuff today, and then we'll talk about some weighting and measuring sound levels. So we have a lot to get through today because I still want to go through it, and it's just kind of this going through the math and going through the understanding of how to do this on your calculator. That I think is important. So, yeah, so that's what we're gonna work on today. So let's pick up where we left off last time. And I know even after just since last class, it's like, man, that was a lifetime ago. It felt so long ago. But let's talk about this anti-log, because this is the one that really, really, really confuses people. So, and I think I said this last time, but when you're given the decibels, but you want to find the intensity or power ratio. So in other words, if you want to, instead of solving for decibels, you're given decibels and you want to solve going back and either getting one of the values or the ratio. So this is a little confusing. It says, no, without knowing what are the other values, you can only find the ratio between the intensity and powers. So in other words, I can't, if I like, we have the I over I naught. If I only have, if I'm not giving one of those values, I can't solve for it algebraically. So I have to just say, what's the ratio of those? That'll come a little bit clearer as we go along, as we work through this. And then the other really, really, really important thing here is that 10 to the x is the mathematical inverse to log 10. So as we mentioned, like before, when we talk about something like, say, what's the mathematical inverse of we could say opposite, but the inverse is the more appropriate term. When I say what's the inverse of addition, well, it's subtraction. What's the inverse of multiplication? It's division. What's the inverse of log? It's 10 to the x, or anti-log. So those are the mathematical operations. So when we're doing these things to one side of the equation to the other, we have to basically apply the same mathematical processes to both sides of the equation. All right, so let's just do this. So what I want you to do, and we did this, we left off on this last time, but let's go through and do this right now, and let's get some points on the board for this. So what I'm going to do is I'm going to go ahead and just run this one right now, and we won't go. We are going to go to the breakout rooms for the other questions, but we did this one last time, so I'm not going to go to the breakout rooms for this one right here. But I'm going to tell you how to do it. So basically, you just go to your computer, you go to your calculator or computer if you're using a computer calculator, and you type in 5 10 to the x, or depending on if you have another calculator, you could go 10 to the x 5 enter. Could be the one there. But basically, what we want it to look like is 10 to the 5th. Is what we're saying. What we're really doing is saying 10 to the 5th. What is 10 to the 5th? And the answer is, yeah. Does anybody have any questions on their calculator? Have any snags with that? Yeah. Okay. Okay. Get on it. Uh-oh. Okay. Well, worst case, just use your computer if you have to. That always has good calculators. No, this is not the EE. This is the 10 to the X. So, yeah. Are you using a computer calculator or a physical calculator? Okay, yeah. So that one, you see the 10 to the X button? Yep. So remember, what we're doing here is essentially it's anti-log. So that's the inverse log. So if you like, while we're waiting for everyone to get caught up on this, what I want you to practice there is, so if you hit 5 10 to the x, it gives you an answer, then take the log of that. So then take the log of that value. So in other words, 10x and basically you can toggle back and forth between the log value and the 10 to the x. And you can see that it just switches back and forth. Oops, hang on. Let me navigator. All right. Let's see. I think we need to get moving on here. I know that if you're still trying to get logged in and get it paid for, it's okay. We gotta get moving on here. You might miss this one question. That's okay. Well, what I would do is just, well, I guess you can't even get logged in without it. So, we'll have to move on for this one right now. But like, if you miss one question, you know, we do enough of these over the course of the semester. Missing a question or two it's gonna come out in the wash. So, all right. So let's stop this up and let's take a look and see what we got here. Yeah. Look at y'all. I'm so happy. Ding. Usually have like when you get to critical listening, you'll have me for critical listening next semester. And if everybody in the class gets it right, y'all get a ding of joy. And it's super fun to get the ding of joy. Right, Carter? All right. So indeed, it is 100,000. It is 100,000. And we can see also that 10 to the x is also, we can say it's 1 times 10 to the 5 is 1 times 10 to the 1, 2, 3, 4, 5. So it's 1 times 10 to the 5. Cool. Okay. We've done this one before, but let's actually go through and do the math on it. So if you want to, and what I encourage you to do is try to beat me to the answer by doing this yourself. So I'm gonna walk you through doing this. I'm gonna do it just on the screen right here, and then I'll do it on the iPad as like the way I would actually write this out. But let's take a look at what I'm asking, and then we'll run through this. We'll walk through this by ourselves. So here I'm saying dB equals 10 log L2 over L1. And in this case, you're like, well, what is L2 and L1? It doesn't really matter because all we're talking about is like the change. And I'm using L as a placeholder for level. It's just a level of some sort. It could be in some sort of power level. So that's all I'm really saying here. And because it doesn't really matter. These are just placeholders because we're not going to actually be able to solve for those actual values. And I think using L2 as just generic levels. So what I'm asking you though for is if I take this and I take 3 dB. So what I'm going to do is I'm going to put 3 decibels in there. But what I'm going to solve for is this relationship right here, this ratio. Because I don't know which either one of these are, all I can solve for is the ratio relationship between the two of these. So what I'm trying to, again, just to kind of be clear here, what I'm trying to do is solve for L2 over L1. That's the ratio. And so I have three on the left side here, I have 10, and the log of this value right here. So the first thing we want to do is we're going to, on this right here, we want to divide both sides by 10. Because what we're trying to do is isolate this right here. So to get rid of this 10 right here, we divide this side by 10, and we divide this side by 10. And the result is we get 0.3 on the left here, and then the 10 is gone over here. That's just classic algebra right there. And then now what we need to do is we're trying to solve for this right here. And remember that to get rid of this log, we have to apply the anti-log to both sides. So by applying both sides to 10 to the x, in other words, I take this value 10 to the x and take this value 10 to the x, the log and the 10x will cancel each other out, and then I'm left with a 10 to this value over here. So the result is it looks like this. So by doing inverse log, and I get it. Everyone's like, wait, what? So what I'm doing is I'm applying inverse log to both sides. Remember, 10 to the x is the inverse log. So by applying inverse log here, this goes away, and then 10 to the x is inverse log is 10 to the x is inverse log, and so 10 to the 0.3. So what I do is I take L2 over L1 is 10 to the 0.3. And if you take 0.3 and hit the 10 to the x button, you end up with, well, I just flipped the other side. I can leave it like this, but because this is what we're solving for, I'm going to put this on the left side. So now it's just 10 to the 0.3. And then the result is it's 2 to 1, or actually the level is 2, right? So it's the answer is 2. I don't know why I wrote it like that. I should just say it's 2. It's actually not quite 2. It's a 1.99 or something like that. What's the actual number? What do you guys have for that? Yeah, okay. So what that's telling us is that you could say this is 1.995 over 1, That's the same difference. But what we're really telling us is that this value right here is 2. Well, I'm just going to round it to 2 for right now, just to keep things simple. But what it's saying is that this level 1 to level 2 has a ratio of 2 to 1. Whatever the value is here, you can put it over 1. So if this value for whatever reason was 4 or 5 or 6 or 5,000, it'd be a 5,000 to 1 ratio. So 5,000 divided by 1 is just 5,000. So in this case, 2 divided by 1 is just 2. So what we're saying there is that it doubled in value. And this is something that we know. We worked this last time. So if I went from 2 to 4 or 4 to 8 or 8 to 16 or 5 to 10, all of those are going to give me a ratio of 2 to 1, and which are also going to be represented as 3 decibels. So what we're saying there, the bottom line here is that 3 decibels represents a doubling. This 2 means it went up by a level of 2. So that's all I'm really saying here. And I know that this can be kind of confusing, but that's all that's really saying. So let me do this real quick. I'm going to just do, I'll do it one more time on the iPad so we can see it. Let's see, I've got to move this thing out. My new share. Okay. And I'm going to do this one again, but I'll do it here. Okay. So what I said is I'll do it like as if I were doing this by hand. I said 3 dB equals 10 log L2 over L1. So this is what I'm solving for right here, is what I'm asking for. Is I'm asking for that ratio. So what I want to do is divide both sides by 10. So I would divide this side by 10 and this side by 10. These 10s cancel each other out. And I'm just going to get rid of the dB right there. So I'm left with, the result is 0.3 equals log L2 over L1. Then now here's the one that always gets everybody, is that I'm going to take this whole thing and do this 10 to the x. So 10 to the log of, and I do the same thing over here. And the result is that, because by doing this 10 to the x on both sides, these cancel each other out. And I'm left with 10 to the 0.3 equals L2 over L1, which is the same thing as if I write it like this, L2 over L1 equals 10 to the 0.3, which I can say is 1.995. So what I'm saying in the end is L2 divided by L1 equals 1.995. And that, my friends, is basically just showing that it doubled in value. Wow, my handwriting is really bad. Sorry. So, yes. Lucero, yes. So basically X being the number that is in the antilog. Good question. So basically the 10 to the X is the thing that's going up there. Cool. Let's go back to some PowerPoint here. Okay, so let's do this again. What I want to try, this isn't, like, I want you to try to beat me to the answer. So right now on a piece of paper, try and blow through this and figure out, because what we want to figure out is like, how much change is decibel? Or what we could also say, what's the magnitude of change? That's another term we might use for it. But we're saying, essentially, what's the ratio? How much change is 40 decibels? And if we think about like what 40 decibels really is, so something like, say, a microphone preamp. So a microphone preamp will oftentimes use 40 dB of gain. If you're using a dynamic microphone on a reasonably loud instrument, we'll say like a trumpet. So you may put something like between 30 and 40 dB of gain on a microphone, like say SM57, for instance. So what we're saying there is, well, okay, how much change is that? So let's go ahead and let's run through this and like go through this and see if you can beat me to the answer. So we set this up by saying dB equals 10 log L2 over L1, because what we're solving for is this how much change is this one right here? That's what that is. So then I'm going to drop in a 40 in there, and we divide both sides by 10. So I left with a 4. And again, once again, this is the tricky part, is you take both sides 10 to the x, or anti-log, And the result is I get the log goes away. So I'm left with L2 over L1 equals 10 to the fourth. And then we go, okay, so I'm flipping just the equation just so that it makes a little more sense. I could leave it just like this and just continue that way, but I just like, generally speaking, we like to have like what we're solving for and then the answer. And then and this one actually, you don't even need a calculator for it, but go for it. Type 4 10 to the x is 10,000. So let's pause for just a moment and think about what I'm saying there. So let's go back to that example I was saying that, okay, if I have a microphone preamp, so when I sing into a microphone, well, I guess I have my my trusty AT4040. That's what I'm talking into right now, right? And so this is a pretty sensitive large diaphragm microphone, but I'm going to use the example of like using a dynamic microphone. So because the dynamic microphones are much less sensitive than a condenser. So a condenser in this case right now, I don't need to add a whole lot of gain to it. I'm probably adding, actually, I can look it up right now. I'm adding 20 dB of gain on this microphone right now. So what that's saying is that this microphone is outputting, like when I speak into this microphone, it's outputting a voltage. That little voltage is going through the wires on your XLR cables into your mic preamp. But to get that mic preamp up to, or to get that gain of that super small little signal inside of that microphone cable, it needs to get up to what we call line level. And to boost that signal, so we have to boost that signal a bunch. In this case, I'm boosting this one 20 dB, but we'll use what I have on screen as saying 40 dB. So a microphone, for instance, like I said, a Shure SM57 on a trumpet would probably be, actually that's probably, yeah, that might be about right. Well, 40 dB might be a little hot, unless it's like a trumpet player with a mute or something like that's kind of quiet. And so what we're doing is we need to add 40 dB of gain. So in other words, that microphone, the super small electrical signal coming off the microphone needs to get boosted by 40 dB to get to what we call line level. And to do that, what we're doing is we're boosting by 40 dB here. What we're doing is we're boosting that signal 10,000 times. Think about that for a moment. Holy crap. We're boosting that signal 10,000 times what its original value was. So it's coming at 0.0001 volts, and we're trying to get it up to about, well, actually 0.00001 volts, and we're trying to get that up to about 1 volt. That's crazy. So this is a huge number. I mean, it's hard for our human brains to even consider multiplying something by 10,000, what that actually represents. But this also explains, in part, why good microphone preamps are so expensive. Because to make a good microphone preamp, you're boosting the signal 10,000 times. That means if you have any mistakes in your circuit, those also mistakes get boosted 10,000 times. So to amplify a signal 10,000 times is no small effort. And so you can do it on like pretty expensive IC chips, but you can also use really expensive transformers and discrete electronics to bring it up. And so this is what you're paying for. When you go spend a lot of money on a microphone preamp, what you're paying for is the electrical engineering that has to go into figuring out how to boost its signal 10,000 times very effectively. So yeah, okay. So what we're saying there is that, yeah, if I put in 0.0001 volts, outside is going to come out 1 volt. So this is just the ratio of the input to the output. So whatever the input value, the L1 value is, it's multiplied by 10,000 times to get the output value, or the second value. So yeah, just to be clear here, all I'm saying is the L2 over L1, those are generic placeholders. That's all I'm saying there. Okay, let's do it one more time. I'm just going to do this one because I want to get things moving along here, but 23 dB represents how much change. So we were using some pretty clean numbers before, but if I do this, dB equals 10 log L2 over L1, 23. So 10 log L2 over L1, so we can divide both sides by 10, and I'm left with 2.3 equals log L2 over L1. Then I'm going to take an anti-log of both sides, and I get 10 to the 2.3 equals L2 over L1. And then now if we just do 2.3, 10 to the x, we get 199.526. Okay. So just for a sense of scale. So when I said 40 dB was 10,000 times as a 10,000 fold change, 23 dB is a 200 fold change about. So what we're doing is we're using decibels to represent how much change there was. And so that's essentially what we're trying to do. And that's really what I'm trying to like beat in here, is trying to like being like, yes, what we're using is the amount of change, and also just starting to see the sense of scale. Okay, let's do this one. What we're gonna do a clicker one, but I want everybody. We're gonna do this one as a breakout room one here. So I'm gonna go ahead and start this one right here, and I'm gonna send everybody off into breakout rooms. Where's this? Breakout rooms. Okay, so let's get this set up, and I want you guys to run through this. There we go. We have a bunch of people here today. So I'm going to send you to the breakout room. I'll give you a couple minutes here. If you get it, like, help each other out. First, go through the thing, get your answer, and then help each other out. Make sure that everyone else has the same answer. If we have enough time, help each other out and try and explain how to get this answer. If you understand this stuff, please try to explain it to somebody else. If you need to, if you're all lost, come back and ask me for help. But I'll give you, like, let's see, we're already 1 minute in right now. So please spend about another 2 or 3 minutes. I'll give you 2 minutes, and then I'll hit the marker to come back. So why don't you go for it, please? All right. Get everybody clicked in. Last call. Yeah. Nice. So I know this is confusing, but how are we feeling on this? Cool. Yeah. hmm Cool. Okay. Well, and for everyone that's saying it's simple, I know there's a whole bunch of you out there too that are going, I don't like it. I don't get it. And that's okay. So what I really want to do is, and I just, what I want to try to do is what glean is the important, what is it actually telling us? You know, like the math is all one thing, but what is it really telling us? And so like in this case right here, 35 decibels represents what magnitude of change. So in other words, when I say magnitude of change, I'm just saying the ratio. How much change is it? Is it how many fold it? In this case, it's a 3,000 fold change, or 31. It's like it's 3162 times the original value. So if I have a microphone preamp set at 35 dB, what it's doing is it's boosting the signal 3,162.3 times of the original value. That's what it's doing. It's boosting that signal. It's an amplifier. So in this case, it's because 35 dB is going up. It's doing that. Cool. All right. So, there's an interesting thing. There's an interesting quirk here, though, and this is a bit of a wrinkle. So just when you start to feel like you're kind of getting the hang of this stuff, I'm going to throw a little wrinkle into the system here. And the thing is that when we measure what we call power, so the decibels always relate back to power. And this just has to go back to the bell, back to the actual bell, which is named after Alexander Graham Bell. That's what the bell is in decibel, is Alexander Graham Bell. And this whole system is based off of the old telephone systems. The original, actually, I think it might even be telegraph systems was the first system that this was based off of. But these were developed around, like this mathematical system was developed around like electrical signals. But the thing is, and it was developed around this notion of what we call power. So power is like watts or intensity, which is watts per meter squared. But the problem with that is that it's very difficult to actually measure power. We don't really measure power directly. So we can only measure power indirectly by using stuff like pressure, voltage, current, and particle velocity. So what we're going to do, so like this right here, I wrote this down. I underlined it, but this is important, but not so much that you like it burned into your brain. But intensity and power are proportional to the square of the pressure, voltage, and current of the particle velocity. In other words, let's say that basically you have to square this thing. So in this case, pressure. So if I start right here, if I go dB equals 10 log. And I did this all official with a base 10 log right here. But normally, you know, I don't write this 10 here very often, just because like everything we do in this class is going to have a log base 10. So I just wrote it to be official in this case. But right here, I said p squared over p squared naught. So what we're doing here is that basically, remember I had intensity in here, or watts in here, power in here. So capital P stands for pressure, not for power. That's important. So powers in watts. So in this case, what happens if I want the pressure is squared pressure is proportional to the watts. So if I want to put pressure in this equation right here, I have to square the top and square the bottom, which seems a little bit strange, but stick with me, bear with me on this right here. And I'm just going to throw I'm not going to do quite a sleight of hand here, but what we can do, there's this mathematical rule. Basically, if I take the square up here, what I can do is I can take the square of this and the square of this and pull this out, and it becomes a 2 over here. Because, well, I don't want to spend too much time on it. I'm going to ask you to take my word for it. If you want to spend the time and work out the math for it, go for it. But what happens here, if you watch what I do here, I'm going to take the 2 off of here, take the 2 out of the exponent here, and put it in front of here. And the result is I get dB equals 20 log times the P over P naught. And so what we see when we're talking about pressure is that it's a 20. So basically it's a 20. We put a 20 here instead of a 10. And so this is true for most things that we measure. So, what did I say here? Oh, I could also say, so P here. So I use P naught with a P sub 0. And then I also say that this is just the measure value. I could also say something like starting and end value. And so that's the same thing. So I said P1 over P2, where I said P1 is the initial pressure and P2 is the ending pressure, like the start pressure and the ending pressure. So state 1 and state 2, the input, the output, those kind of things. So we can measure that. But what the important thing to understand is when we talk about pressure is we put a 20 here. And that makes things kind of confusing. So if we look at this table right here, and this is taken from the book, but basically that there's times we use the 10 log of this, and there's times we use the 20 log. I'm not going to ask you to remember this. I'm not going to quiz. Well, maybe actually, I'm sorry. No, actually, I do. I'm not going to ask you to memorize this, but I do want you to know this stuff. And so that you look up this table. You can look it up in the book because I think there is a homework question on this one. There will be a homework question on this. But if we look at like the different things we measure, so we measure in decibels, we tend to measure things like acoustic energy, and we measure electric energy. We also can actually talk about stuff in terms of distance, in terms of SPL. But if we look at these ones right here, so we look at acoustic intensity is watts per meter squared. That uses a 10 log. Power is in watts, so that gives a 10 log. Air particle velocity is given in meters per second, which is going to be done in 20 log. And pressure, which is in Newton per meter squared, is going to be in 20 log. So then we do over under electrical power, watts, we see that we have both acoustic power and electrical power in watts. So that's a 10. But we have current, which is amperes, is going to be in a 20 log, and voltage, which is going to be a 20 log here. So that's interesting. So this is so what I want you to take away from this thing right here is that when we do voltage, which is what we usually use when we're measuring stuff, most of the time when I'm measuring stuff in the studio, I'm using a voltage meter, a voltmeter, which I don't have one. Well, I have a bunch of them, but they're just not in this room right with me right now. A voltmeter is going to be using, whenever we use voltage, we just use the 20 log version of this thing. So that's important right there. And so like in this case, I'm using V2 over V1. I would say the reason I did that shaky thing is because this is the one that I use. This is by far the most one that I use almost all the time. When I'm talking about voltage, because I measure with the voltage meter, and I use a 20 right here. So when we talk about things like faders on a console, what we're looking at here, and this is just like a value, and this is one of those things that like I had never really understood. This is actually not very good representation right here, but we see that we have this what we call unity. When go next time you're in your DAW in Pro Tools or Ableton or whatever you're in, go look at your fader and look at it very closely, and you'll see that it's going to have a 0 mark right there, and it usually is going to go up to +6. So it's actually it rarely goes up to 10 right here. So this is going to be 0, and then these are all going to be negatives. So this is actually between -10, 20, 30, 40, 50, 60. And what that's telling us is that if I put this thing at 0 right here, what that means is that move that out of the way, that the voltage input is the voltage output. Because if I do V2 or V1, and we'll just call it 1 volt, it doesn't matter. If I put 1 volt in and 1 volt comes out of the console, then the 1 divided by 1 is 1. Take the log of 1, which is 0, and 20 times 0 is 0. So that means it's a 0 dB change. So when I go up here, if I boost this thing, it's going to go up. That means that that this is going to be larger, that the output is larger than the input. So that's going to be a boosted signal. And then down below here, it means that the input value is going to be larger than the output value. And so this is going to be a decimal point, which is going to result in a negative value, which is going to be down here. So literally what we're saying here, but I just wanted to make this clear because this is something that was like strange to me when I was starting out. I didn't really understand what the numbers on the fader meant and what that meant right there. And so the reason we see that this as a 0, we call that unity, meaning that the input is equal to the output. And so whether you're working on an actual physical console or you're working your digital console, like in say Ableton, for instance, and you have your little fader right there, that when you're playing back that waveform, that audio file, that the gain from the input to the output is exactly the same. So it's not changing any of the gain as it goes in or output on there. And we can talk about the terms of dBFS, which is digital decibels. dBFS is, but that relates back to voltage. So we use this one right here is going to be the one we use the most. What else do I have on here? Oh, I shook this one again. I just want to make that clear. Okay. So I'm just going to I'm going to run through this equation. I'm going to blast through the couple of these really quickly just so you can see how it works. If I have a 1 volt VRMS at the input and a fader and a level of -10, what's the expected output on there? So what I'm going to do in this case, now what I can say is, okay, I'm solving for decibels and, I'm sorry. No, the decibels is -10 and I'm giving a 1 volt VRMS at the input, which is right here. I can solve for the output right here. I'm just going to show you this. I don't want you to actually do this math. But so -10 equals 20 log V over 1. It's 1 volt VRMS, and this is -10. That if I go through and then divide both sides by 20, so I get -0.5. And then basically 10 to the -0.5 is that. And then because I have just a 1 over here, I would multiply both sides by 1. So that V2 is going to be coming out as 0.3 volts. So if this is 1 and this is negative 10, this is 0.3 volts right there. Interesting. Well, maybe you're like, that's not that interesting. But I think it's interesting. And what I think is interesting is when you actually do this, like actually take out a multimeter and actually practice this stuff. If you have a physical console and you have a multimeter, try doing this. You just run a sine wave through it, measure the sine wave on the output, run it through a console, and measure the sine wave on the output of the console, and you can figure out exactly that it matches up. And it's like, it's so fun when it happens. You're like, wow, this is so cool. It actually makes it, like you can actually see like the numbers work themselves out. It's like magic. And I will tell you this, if you can get through this stuff, you will be heads, like I won't say heads and shoulders. You're going to be better informed than probably 90% of our industry. Most of our industry people, they throw these numbers around like, yeah, boost at 6 dB, reduce at 3 dB, change this. Like, can you give me like 20 dB of gain? Or how much gain does that amplifier have? And most people have no idea what they're talking about there. So this is important stuff. Okay. So here's an interesting one. If I have 1.23 volts VRMS at the input and 0.6 VRMS at the output, what is the gain change? So in other words, this is my V1 and this is my V2. So I can actually go through and go, okay, so in other words, 1.23 volts at the input and then 0.6 on the output, or 0.06 on the output right there. And so I'm going to do 0.6 divided by 1.23. So it's just 0.04878. Take the log of that value, which is going to be a negative value, and multiply that by 20. And I'm left with a negative 26.4. So what that means is that if I'm putting in a 1.23 volts VRMS and on the output I'm getting 0.6, that if I look over, I'll bet you my fader is going to sit right at negative 26.24 dB. So that's what it's doing. It's attenuating the signal by 26 dB. By 26 dB. Cool. All right. Let's shift it like in like action movies, whatever, like there's always the car chase scenes. And for whatever reason, they always seem to be like shifting up. Like unless like they're trying to be like really accurate, but nobody downshifts. Like I was just watching Ford versus Ferrari this last weekend. Great movie, by the way. You're like, I always think it's funny when their car races are going like head to head. And then all of a sudden they just shift it like one more deeper and they pull out. You're like, why didn't you just do that the whole time? Like, it's always like they're like waiting, they're holding back. And then all of a sudden they're like, they got this secret weapon of shifting one more gear. And they're like, aha, I gotcha. But like, I think it's funny, like how they always tend to be shifting. And if you watch, like, this is a little audio trivia, cause you're like, why is he talking about car racing right now? But this is audio post-production. If you're watching a car racing scene, they're almost always accelerating. Listen to the sound next time you're watching a car racing, or not a car racing scene, but an action scene. They're almost always accelerating. It's it just seems like they're always like they have like infinite number of shifting gears. But what we're gonna do right now is we're gonna do that. We're gonna add this one more in there. We're gonna shift to 6th gear right now. We're gonna shift it down in here and go. Okay, let's ratchet this up one more level. You're like, what? How could this even? You mean, how could this go any further? This is like the limit of all things decibels. Nope. We've got some more levels to go to. And what we're going to do here is we're going to call what I call decibel flavors. This is an important concept. So basically, up to this point, what we've been doing, and I think it's important to understand that whenever we talk about decibels, we're always talking about a comparison. It's a ratio. We're always comparing two things. That's what a decibel is. But what we want to do now is instead of comparing just the input to the output of something, we want to compare it to a reference value. So with this, what we're going to do is we're going to use reference values. So right here by flavors, I mean using a reference value as the initial state, or what we call it in the denominator right there. So the reference value there. So we only need a single value to compare to the reference value. So basically, I'm giving you, like, instead of like I2 over I1, I'm going to give you I1. That's the reference value right there. So when we talk about things like electrical decibels, so we use electrical decibels, acoustic decibels. There's all sorts of different kinds of decibels out there. But in decibels, we call this things like, we have things called dBm, dBV, and dBu. And if you look on the back of your Pro Audio gear, or you'll see this thing right here, +4 dBu. And then if you look on consumer gear, you'll see it's -10 dBV. What these are is they're saying that like these are specific flavors of decibels right here, and they're implying that they're using a reference level. So instead of comparing it to input to output, we're comparing it to a reference value. So just like I'm saying, we always use decibels are a comparison. Now what we're going to do is we're going to compare it to a fixed value. So whenever you see a dB something, dB like dBu, dBm, dBV, there's all sorts of decibels out there. dBFS, you're going to see that it relates. Like whenever you see these values right here, what that implies is that you have a reference value in the denominator. So let's look at acoustic decibels. And here we say dBSPL and dBSIL. These are things that we actually kind of like are used to thinking about. dBSPL. So when we say what's the SPL of something, what we're saying there is what's the decibel right there. And what we're doing is we're comparing it to a reference value. Specifically, we're comparing it to the quietest sound you can hear. So how loud is it now compared to the quietest sound that's possible to hear? Rad. I don't know. I think that's like pretty cool. I think this is really neat stuff. So like basically what we're going to do is let's take a look at some of these reference values here. Oh, we also have digital decibels. So digital decibels are dBFS, dB full scale. So dBFS is the maximum output of your system, and then we go down from there. So when we say like we talk about like in mastering, for instance, so dBFS, like I master my stuff at say or whatever, like the new systems are going to be minus 14. It's actually a little bit more complicated than that, but we say it's minus 14 dBFS RMS, or we say minus 6 or minus 8. What we're saying there is that the maximum or the maximum output is 0, and we're comparing the current level to the maximum output in dBFS. Pretty sweet. So let's take a look at this. I'm going to run through some of these right here, and I'm not going to ask you to do. I'm going to ask you to do some of these, but I want you to take a look at this right here. So electrical decibels dBV. This one right here is the consumer voltage one right here. dB with a capital V. So it's written there as you'll see this on the back of gear sometimes. So it's dBV equals 20 log 10 V over V naught, where V naught is 1 volt. So in other words, what we're doing is we're referencing 1 volt. So this is the equation over here. So it's dBV equals dB capital V is 20 log V over 1 volt. So, and because we're talking about voltage, it uses the 20 log version of this thing. And then this is what we use in consumer audio. So if you have like a piece of stereo equipment or like a CD player or DVD player or some of that kind of stuff, what they're doing is they're referencing that as they're referencing it to 1 volt. So in the consumer audio world, we say minus 10 dBV equals consumer line level. So what we can say is that minus 10, if I put minus 10 right here and I solve for this voltage right here, I get 0.316. What I'm saying right there is that gear is expecting about 0.316 volts for its like normal working conditions. Like that's where consumer audio works at. So when you have RCA inputs on a piece of gear, it's expecting about 0.316. And so what we're doing is we're standardizing our line levels so that this piece of gear can talk to this piece of gear without blowing it up or without. So we want consensus among our signal chain, amongst our audio gear, so that everyone's expecting about the same voltage right there. So line level in consumer gear is what we call minus 10. So minus 10 dBV is 0.316 volts. Same difference. So what we're saying now is that 0.316 is minus 10 dBV. Minus 10 dBV equals 0.316 volts. So it's just a different language. It's just a different way of saying things. So, okay, cool. So we already know this because I just told it to you, but what is the VRMS for consumer line level at minus 10 dBV? I'm going to calculate this for you and show you how to do this. So dBV equals 20 log V over V naught. Let me see, what are we doing on time here? Okay, yeah, we're doing all right. I know I'm moving pretty fast here. What I'm trying to do is I'm trying to stop the high points and explain what's going on here. The math I'm trying to blow through pretty quick here because like the math is useful, but it's supporting the what we're trying to talk about here. So dBV equals 20 log V over V naught, and so this V naught right here is a reference value, and we know that because it says dBV that this is 1 volt right here. So let's substitute that in. So minus 10 dBV. And you'll notice that I got rid of the dBV, right? Because that doesn't need to be there. That's not a dimension. Decibels are dimensionless. So I got rid of just the dBV over here. It doesn't need to be there. So minus 10 equals 20 log V over 1 volt. So dividing both sides by 20, I get negative 0.5 equals log V over 1. And then in this case, I'm going to take both sides to the 10 to the 0.5, or negative 0.5, sorry. And I get 0.316 equals V over 1. Now I multiply both sides by 1 volt because I should have written 1 volt right here. But that V equals 0.316. And actually, I'm sorry, this is V equals 0.316 volts. This one does have a value on it right here. So this is 0.316 volts. So that's exactly what we just calculated right there. And that's what I gave you before, but that just kind of proves it, so to speak. Okay, so when I said that we use dBV as the consumer voltage, we use dBu for professional. Why do we have two different versions of it? I don't know. This is just the way it is. There's some historical reason why we use dBV for consumer and we use dBu for pro audio. It's just the way it is. And if you want to fight the good fight and try and merge the two of them together, go for it. But what we do here is for dBu, we talk about pro audio stuff. So because it's voltage, it uses the 20 log, and the reference value is 0.775 volts. So whereas consumer audio reference to 1 volt, pro audio references to 0.775 volts. Why? I don't know. That's a question I have not really figured out yet. It has to do with something with impedance and measuring. It's referencing a different value. But anyway, the thing that we want to remember here is that dBu equals 20 log P over 0.775. Oops, actually that's be V. That's a voltage right there. That's a mistake. My bad. 0.775 volts. So used primarily in pro audio. So what we look at is pro plus 4 dBu is considered pro line level, which is 1.228 volts. So we saw that consumer pro level, the reference level is 0.3 volts, whereas pro audio is 1.228 volts or 1.3 volts. So it's an entire volt higher for consumer. And this kind of explains why you can't plug in pro audio gear to consumer gear and consumer gear to pro audio gear. But we'll get to that in a minute. So I'm going to do this math again, just once again. What's the VRMS for? And you would think, what is this RMS right here? RMS is going to be root mean square. I'll talk about that here in just a little bit. But what I want to say is, what's the VRMS for pro audio line level at plus 4 dBu? So what I'm going to do is I'm saying dBu equals 20 log. I want to solve for this value right here. Because this is a dBu, we know that this is a 0.775 volts right here. Because anytime, just to reiterate this, anytime I say that I have a flavor, so the flavor I'm talking about right now is dBu. Anytime I have a dBu, that implies that this is 0.775 at the bottom right there. So I'm going to, with this in, plus 4 equals, and plus 4 is just 4, equals 20 log V over 0.775. So then I'm going to go divide both sides by 20. So 4 divided by 20 is 0.2. And then I'm going to take the inverse log, anti-log of both of these. So 10 to the 0.2 equals V over 0.775. And the 10 to the 0.2 is 1.585. And then I have V over 0.775. So I have to multiply both sides by 0.775 to solve for V. So what I did is I moved this 0.775 over to that side. So 1.585 times 0.775, and I get 0.316. Wait, nope, that's not right. That's actually 1.223. I'm going to change that. I got to fix that. That's annoying. I copied and pasted. Right? Cool. All right. Let's blast through that. Cool. Proved it. So 1.585, and that's actually volts. I'm sorry, I should have written volts right there. Okay. I'm just going to blast through this one more time. And I want to say, what's the difference between minus 10 dBV and plus 4 dBu? Now, if you're looking at this, you may be like, well, intuition would tell us that it's 14 decibels. But it's not quite that. So because we're using different values here. We're using different reference values. dBV is not the same as dBu. So to compare these, what we have to do is we have to go back to their voltages and compare the voltages, because we know that this is 1.228 volts and we know that this is 0.316 volts. So that's what we need to be comparing. So let's do this. Remember, plus 4 dBu is 1.228 volts and minus 10 is dBV equals 0.316 volts. So what I want to do is I'm going to do dB equals 20 log V2 over V1. Which one's the V1 or V2? Doesn't really matter. So in this case, I'm going to do 0.1 or 1.228 on the top and 0.316 on the bottom. If I were to flip these around, all you get is you get a negative value or a positive value. So what I'm doing right now is I'm comparing line level of pro audio gear to line level of consumer gear. So 1.228 divided by 0.316, take the log of that, get 0.5895 times 20 equals 11.79. So what we're saying here is that so line level for consumer gear and line level for pro audio gear has an 11.8 dB difference in gain. So what I'm saying here is if I hook up a consumer CD player, say I go to Best Buy and buy just some off the rack CD player that has RCA outputs, and I put that into my console, it's going to be really quiet. It's going to be too quiet. It needs 12 dB of gain. On the flip side, if I hook up a mixing console to my home stereo, and my home, it's going to kick it out way too loud. It's going to be 12 dB too loud. It's going to be, everything's going to be like blowing up, saying bright red, saying like clipping and all these bad things are happening. So what you need to do is if I'm going from consumer gear to pro gear, I have to add 12 dB of gain. And if I'm going from pro gear to consumer gear, I need to cut, I have 12 dB attenuation, or I need to reduce it by 12 dB there. So there's a 12 dB difference between consumer and pro levels. Yeah, if you plug in your pro gear into consumer, it's usually too hot. And if you plug your consumer gear into pro, you usually need to boost the levels by 12 dB. So interesting, kind of cool stuff there. All right, let's take a look at a couple other decibels. We're going to spend more time on these other decibels coming up next week when we start talking about perception, because I think this is when we start talking about decibels and hearing, the hearing system, it's fantastic. It's amazing stuff. It's really cool. So when we talk about acoustic decibels, so dBSIL, so we say SIL, is it sound intensity level. This intensity business right here goes back to, it uses a 10 log version of it because intensity is in watts. So when we talk about dBSIL, it uses the 10 log version of it. But here's where we start using scientific notation. So the reference value is 1 times 10 to the negative 12 watts per meter squared. So that's this reference value. Remember, this is a flavor. The flavor of the dBSIL I'm talking about right now is dBSIL. And because it's dB with something right here in this SIL, implies that the reference value is 1 times 10 to the negative 12 watts per meter squared. What is this value right here? That's the threshold of hearing. That's the quietest sound you can hear. So this is interesting. It's 0.00000000001 watt per meter squared is the threshold of what we define as the threshold of hearing. Well, we're going to deal more with that coming up soon. But and then the threshold of pain is 1 watt per meter squared. So that we can see that there's this is such a huge scale from 1 to 1 times 10 to the negative 12. That's the range of human hearing. That's huge. That's crazy big. So let's take a look at this. So right now, 5 times 10 to the negative 5 watts per meter squared is how many dBSIL? So what I'm going to do is I'm going to go dBSIL equals 10 log I naught, and I naught, because this is dBSIL, we know that this is 1 times 10 to the negative 12. How do I know that? Well, it's because you can look it up in a book. Like that's the reference value. I'm giving it to you, but like you can go look it up anywhere and figure that out. So what I'm saying is dBSIL equals 10 log 5 times 10 to the negative 5 over 1 times 10 to the negative 12. So this gets a little confusing, and this part can be kind of tricky. So how do you do 5 times 10 to the negative 5 divided by 1 times 10 to the negative 12? Well, this is where you have to get pretty good with your order of operations on your calculator. So the way I would do this is I would go 5 negative 5 divided 1 negative 12, enter. And that will give you that value right there. There's some shortcuts here you can do. And I'll tell it basically when I divide this, I can subtract negative 5 minus negative 12 to get the exponents. But I would say just believe in your calculator. And we can go over the calculator stuff in a little bit. But I just want to get through this content right now, and we can work through the mechanics here in a little bit. So what I do here is I go 5 times negative 5. So 5 times 10 to the negative 5 divided by 1 times 10 to the negative 12 is actually a very large number. It's crazy. You have the small number divided by a really small number gives you a very big number. So 5 times 10 to the negative 5 times 10 to the 7th. So 5 times 10 to the 7th. So if I want to, I go 5 7, enter, and then I take the log value of that. I'm going to get 7.7 times 10, which is 77 dB. So what we're saying here is that 5 times 10 to the negative 5 watts per meter squared is 77 dBSIL. It's just a translation. So so what we end up saying is that we use dBSIL. What we're talking about is watts per meter squared, but we're using dBSIL because this makes a lot more sense for us to talk about it than it is in these super, 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 super tiny little numbers right there. All right. So if I want to work it back the other direction, I go 65 dBSIL equals how many watts per meter squared? So in this case, I'm given this value right here, and I'm going to solve for this value right here. So I just substitute in. So 65, and I'm just going to wait for the 1 times 10 to the negative 12. I'm going to wait to substitute that in. So 65 equals 10 log I over I naught. So 6.5 equals log I over 1 times 10 to the negative 12. And I'm just going to do anti-log on both sides. So I get 10 to the 6.5 equals I over 1 times 10 to the negative 12. And now I'm going to go, so when I do 10.65, 10 to the 6.5 is 3.16 times 10 to the 6. It's kind of crazy to think about that. But if I type this out and I go 6.5, 10x, I get 3.16 times 10 to the 6. So now, and I'm multiplying both sides by 1 times 10 to the negative 12. And then the result is 3.16 times 10 to the negative 6 watts per meter squared. So it's just like a translation tool. What I'm doing here, it's a pain. And there's online calculators for this sort of stuff. But basically, we're just saying we're converting between watts per meter squared and dB. Watts per meter squared and dB. Because it's dBSIL, we know that it's going to be 1 times 10 to the negative 12 watts per meter squared is the denominator, the reference value. Okay, I'm going to move on because I don't really have time. Like, I'm going to, like, basically, well, okay, let's take a look at this. 110 dBSIL. What's the intensity in watts per meter squared? Well, let's start off with this question right here. Is 110 dBSIL? I'm not going to do a clicker for this one. Is the 110 dBSIL loud? Yeah, it's loud. 110 dBSIL is stinking loud. What is it in watts per meter squared? Well, if we go through and we do the math and work it backwards, like basically we find out that it's 0.1 watt per meter squared. That's what 110 dBSIL is equivalent of 1 watt per meter, or sorry, 0.1 watt per meter squared. That's how much energy is going into your eardrum right there. And that's a lot. Considering that the threshold of pain is 11 zeros with a 1 all the way over here. So this is really loud. 120 dB is like really, really, really loud. This is going to be the loud parts of a loud concert. Cool. All right. I'm just going to blast through this because I think we're getting kind of tired of this. I know I am. But I want you to have all this information right there. So acoustic decibels dB SPL. This is the one that we tend to think about the most often. When we talk about like how loud something is, when you like use a SPL meter or the sound level meter, what we tend to think about is dB SPL. So P is pressure. Because it's pressure, it's a 20 log. And the reference value, SPL, is 2 times 10 to the negative 5 pascals. Oops, that's supposed to be a... Man, I really screwed this up. That's supposed to be a P. I can't change that very easily. I'll change it in the PDF. So I do post all the... Just remember, I post all the PDFs of all my slides of every class. So if you need to refer back to this, all these slides are available like after class. It takes a while for these classes to render, and so then I post them usually at night. But yeah, this P right here is implied for pressure. So this is 2 times 10 to the negative pascals. So we use the 20 log version of right here. And whereas 1 times 10 to the negative 12 watts per meter squared is the threshold of hearing, 2 times 10 to the negative 5 pascals is the threshold of hearing in terms of pressure. So the threshold of pain is about 20 pascals. All right, I'm just gonna blast through this. 0.8 pascals is how many dB SPL. You can look at this stuff in reference later. We've done this. We've been going through these equations a lot at this point. So what I did right now is I said 0.8 pascals is this one right here, and 2 times 10 to the negative 5. So 0.8 times 2 divided by 2 times 10 to the negative 5 is 4 times 10 to the 4th. Take the log of that. I get 4.6 times 20 equals 92 dB SPL. So 0.8 pascals is 92 dB SPL. Whoops. So we can work it backwards, but I'm not gonna go there because I want to move on here. But what we can talk about are these thresholds right here. So this goes right where I was just talking about a second ago. So the threshold of hearing, the bottom threshold right here is 1 times 10 to the negative 12 watts per meter squared, and this is 1 watt per meter squared. In pressure, I go 2 times 10 to the negative 5 pascals, and the maximum is 20 pascals. And if I put this in the numerator, this in the denominator, I get 120 decibels. If I put this in the numerator and this in the denominator, I get 120 decibels. So what we say is that the threshold of hearing is 0. That's defined. And then our maximum is, well, we call this the threshold of pain. You can hear there's larger sounds than than 120 dB, but you don't want to be anywhere near them. I think so. Krakatoa is the largest recorded sound ever on the planet, and that was like in the 1800s or maybe the 1700s. I can't remember. Somebody look it up for me. How loud was Krakatoa? It's on Wikipedia. Oh yeah. So looking at your notes there. Sorry guys. I know it said basically that you're not getting a chance to apply this, so I'm not retaining it. I totally get it. So what I want you to understand is like we want to go through the math here a little bit, but I'll try to really highlight the things I want you to retain. So I apologize that I know that I'm blasting through this stuff because it's just a lot. So sorry, with the Krakatoa thing, what's the 180 dB? Is that what it was? Yeah, that's a 18. Okay, 1883 was Krakatoa. It's a volcano explosion and 180 decibels. This is enough that like people out on boats, it blew out windows, it knocked people like blew out your ears. It's bad, makes your ears bleed, and kills things close to it. So 180 dB is like, yeah, and you could hear. I think it was still like something like 120 dB, like 10 miles away or something like that. I don't know. I can't remember. It's crazy. If you've not looked it up before, if you don't know the story about Krakatoa, go look it up on Wikipedia. It's an interesting story. It's crazy. But it's basically saying that this is like from 0 dB to 120 dB. What's interesting about this point right here is these reference values that this 0 dB is not absolute silence. It's absolute silence for humans. You can have negative decibels. We define 0 dB as the quietest sound that a human can hear, but there's quieter sounds than that. It's just that we define it. So the weird thing is with these DBSPLs and DBSILs, they're made up. They're like the reference values. I won't say they're made up, but they're referencing to what humans are. And so the 0 dB doesn't mean absolute silence. It means absolute silence for humans. But there's actually there's sounds that can happen that are quieter than we can perceive. So it's kind of interesting. You can have negative decibels. It's not like things are like sucking up sound. It's actually just quieter than what humans can hear. So 0 dB is the quietest sound that we can possibly hear. So I pulled this from the book. So basically, I'm gonna get this out of here. Basically, it's saying that we have like a standard reference 20 times 10 negative 6 is also the same as 2 times 10 negative 5 is the threshold of hearing. So background studio noise is 10 dB. Yeah, that's quiet. But like as we go up here, we can see the pascals, and we can see that this is going like every time we go up, it's going up a decimal point. So it's 10 times that value right there. So it's going up pretty quick. So quiet resonance of 40 dB, that's pretty quiet. Being in a 30 to 40 dB room is really, really, really quiet. That's most of our like recording studio is going to be around 30 dB, between 20 and 30 dB. That's a really quiet room. But what's crazy is like even just a normal like classroom, even with everybody, like I would normally have my SPL meter and hold this up in front of it during class, and you'd find that even just a bunch of people in the classroom is around 45, 50 decibels. It's crazy. So conversational speech is around 60. Noisy offs around 80, and heavy truck is 100. Yeah, a riveter is 110. You could say that this is kind of like loud shows there. So that's kind of crazy. Okay, there's a couple more things I just want to hit on really, really quick here as we wrap this stuff up here, because I know that I'm feeding you with a fire hose on this one, and I apologize, but this is not going to be how it's going to be the rest of the semester. Be like. Don't stress. Don't fret. You'll be all right. So what we have here is this is a fairly expensive DBSIL or DBSPL meter. And this one's a fairly expensive one. I don't know. I think this one would be like a few $100 for this one right here. And when I turn it on, it has like, I go, for me in my room, that's 80 DBSPL. That's quite a bit. So what we have here is basically some levels. And on this thing, you'll like if you have one, and you can get these for your phones and stuff too. Although I don't trust the phone ones, people use them on their phone. Like you can get a SPL meter, which is I think it's kind of interesting to give you like a sense of scale. But they're not calibrated, so they're not really that accurate. But when we look at this thing, if you want to download one, but if I look on this thing, and you probably can't see it, but it says that it says DBA or DBC. And I want you to understand, this is something I do kind of want you to understand here. We have what's called weightings. So when I go into a room and I set this up and I start measuring the SPL of a room, what I'm doing is I'm listening to all the energy in the room. How much energy is hitting this thing? But the problem with that is that doesn't correlate to how we actually, as humans, actually hear. So our human hearing system, which we're going to start on next week, we're not very linear. We don't hear all the frequencies the same. And in fact, when we hear it louder, we hear it more flat than when we hear it quieter. So what we have here is most SPL meter systems, and you can go buy, this is an expensive one, but you can go buy pretty inexpensive ones of these. And we do what's called dBA and dBc. So dBc is what we do. We listen to for sound pressure levels of 85 to 140 dB, which is ridiculous for using network C. Who does 140 decibels? But this one is for 20 to 55 dB. So we're really quiet. But I've never actually seen an SPL meter that uses dBb. It's always dBA or dBc. So what we say here is that what it's saying right now is it's gonna measure that. This is a frequency right here. So this is frequency on the bottom and amplitude on the top here. That what it's going to do is this A weighting one is going to disregard. It's going to roll off. It's like having a high pass filter on this. It's going to disregard any of the low frequency information. So even though that there's going to be at quiet level, say we're going at 40 decibels with some noise, that it's going to disregard all these lower frequencies because this correlates better to the way that we hear as humans hear. So at quieter levels, this is how our ear perceives sound. And at louder levels, this is about how the response of our ear at the C level right here. Well, when I say C, I mean C right here. So what we're saying here is that if you're using something for quiet, you want to use this one. If you're using something for loud, it's going to be this one. So say, for instance, I play some noise at 60 decibels. And if the A weighting and if I use the C weighting, the A weighting is going to show us a lower value than the C weighting, because C weighting is going to include a lot of this low frequency information right here. So basically, what we're doing here is going to it's just a kind of a weighting system to describe how this stuff works. All I'm going to say on adding and subtracting decibels, this is the last part of the class. It goes back to this idea that if you want to add, if I add something I'm going to give this one to you. If I have 77 decibels playing in a room and I turn on another speaker that's 60 decibels, what's it going to be? Well, it's not going to be 130. It's not going to be 137 decibels, right? So it's only going to be slightly more than 77, which is crazy. So, and we can do this demo sometime, but basically it's slightly more than 77. So the way you do that is you actually have to convert back to the original intensities, add those together, and then convert back to decibels. I'm not going to ask you to do that. I just think it's an interesting perceptual experience, and they talk about it in the book, but it's just kind of crazy. So in other words, what I challenge you to do, if you have some studio monitors at home, play some noise out of there, turn one of them off, and listen to the noise, and then turn the other one on, and you just doubled the intensity, but it just went up by just a little bit. It's crazy. Okay, I'm going to wrap it up here. We're going to talk about measuring sine waves. We're not really going to talk about this. I just threw this in because the book has it. I'm not going to ask you anything about this. We could talk about this stuff, but for what we're talking about in class for right now, it's not going to be really that important. What we care about is this term we call RMS, root mean squared. Basically, we use this term RMS a lot in pro audio. I'll let you read this on your own time. It's in the book, but I'll let you read this on your own time right here. And yeah, so we'll call it there. I just want to leave you with this right here. Decibels are a comparison. That is the biggest thing I want you to remember. It's a comparison. And so anytime you hear the term decibels, what I want you to ask, what is it comparing? What are we comparing? Are we comparing it to the quietest sound we can hear, the voltage, a reference voltage, an input versus output? That's all I want you to start. That's not all. That's the main thing that I want you to take away from this. So when you're out in industry and you're looking at, you see this term decibel written in a book or on a piece of gear, I want you to understand what that, at least consider what that's asking for. And if you want to get deeper in with the math, well, you have to go in the math for now, but that's the biggest thing I want you to remember is decibels are comparisons. All right, my friends, we got to get out of here. I'm going to go ahead and stop the recording, but I'll stick around if we have any questions. I have my office hours going on. So with that.